Well, hello everybody. Welcome to this HiPEAC session about the DaCe project. I am Estela Suarez from the Modular Supercomputing Center, and I will be presenting the project together with my colleagues on the panel. I will give first overview, explaining a bit the context of the DaCe project. Then Norbert Eicher will present software stack and programming environment. Alexander Geis will present performance analysis and modeling tools, and Olivier Marsden will present applications. So they will get into the core of the technical contribution of the DaCe project. And we will have time at the end for a general Q&A discussion and session. So the DaCe project is a EuroHPC project, so funded by 50% from the joint undertaking, 50% by the European funding agencies of the partners involved in the project. So we have 14 partners, and it's coordinated by the Modular Supercomputing Center. We just started, so we are starting today, 1st of April 2021, and we will be running for 3 years with a total funding of 15 million euros. So this project is kind of the continuation of the series of the DEEP projects that started in 2011 with DEEP and have run with 3 series. This is DaCe is then the 4th until now. And the core of all these projects is been developing a new approach for heterogeneous computing. We've been developing the so-called Modular Supercomputing Architecture that I will show you in a couple of slides from now. So DaCe is actually at the intersection between these DEEP projects I just spoke about and the new starting C project. That's the family where DeepC, IOC, and RedC are basically members of. And these 3, all of them are starting today, 1st of April 2021. The idea when we put these projects together was to cover what we consider were major challenges for Exascale, but cover them in complementary research approaches. So DaCe, which is here, the green one, covers the part that takes care of the software stack and the programming environment for highly heterogeneous systems, in particular modular architectures, but heterogeneous both at the computing and at the memory area. Then we have IOC that covers more the IO and data management. That, of course, is also an important challenge for large-scale systems. And last but not least, RedC that develops next-generation European high-speed interconnect that focuses around the BXI network. So all these 3 together try to cover important areas for Exascale, and they all evolve around the concept of modular supercomputing that I will explain you in the next 2 slides. So modular, let's say a modular supercomputer is one in which heterogeneous components are integrated in a particular way on the system. So traditional cluster computers are just general purpose processors in a high-speed network attached to a storage. Now, attaching then accelerators to such a system, you can do it, and that's what most of the people does, is just put them directly at the node attached to the host, like for example a graphic card. What we propose is to have an own module that we call booster for putting together all the accelerators there. So basically building a spatial cluster made of accelerators that is power efficient, and it's also highly scalable to run then your applications that are that have really high parallelity on this part of the system on the booster side, having still attached the cluster to it to run the low scalable, the parts of your code of your workflows that need more single thread performance. So that's kind of a different way of building your system, putting on the one hand side, the general purpose elements, and on the other, more the scaling focused elements. That's when you think about scaling, but there are also the aspects of general application requirements. So you have now new applications that need, for example, large amounts of memory, fast access to memory. That's typically from the fields of data analytics. So you could have a specific module, specific cluster addressing the needs of this part of your portfolio. And you could extend the concept with even more exotic stuff like neuromorphic and quantum modules. The idea is you all together at high level have a highly heterogeneous system, but this heterogeneity is blocked into modules. So each module individually tries to be as homogeneous as possible. What is the advantage then for users is that they have a large pool of resources available to them, and depending on the requirements of the codes, for example, highly scalable codes could be running mostly on the booster, maybe running some single or some serial parts on the cluster. Then you could have data analytic workflows running between the data analytic module, maybe using some quantum module for optimization, and then a deep learning workflow between cluster and maybe some of these exotic modules. So this is just a possible distribution that tells you that each very different kinds of applications can find in this system exactly the resources that they need and can be mapped on the hardware according to their specific requirements. And the mapping, as you see, can be very different for different codes. So that's the concept that we have kind of developed across the deep projects, but we have also realized it now in a production system. And the largest one is ULs at Jülich that consists of a cluster and a booster. The booster is actually per se a very, very large scale system, and it is right now the fastest in Europe. But by being both interconnected to each other, you basically can also run applications across the both parts of the machine. Yeah, and modular supercomputing is not only used in Jülich. You see how we have been developing over the years, starting by the deep projects, realizing them in ULs. Now with the C projects starting to cover more this, or to basically further develop the software sides of the system. And then we have seen that this concept has been taken on by the pre-Exascale system in Italy, Leonardo, and the petascale system at Luxembourg, Meluxina. And we see that also two of the pilot systems that will be, or the pilot projects that are coming up from EuroHPC will also use MSA. Of course, our goal is then to build one of the Exascale systems with this architecture. Okay, so with this very general overview of the background and the concept of modular supercomputing, I would then leave the screen to Norbert to go then into the core of DeepC and cover the software and programming environment.
Okay, so yeah, I have to multitask. First to find my window and then to find the mute button. Okay, but I hope now everybody can see my screen and hear me. So concerning software stack and programming environment, so what do we want to cover in DeepC? So first of all, let's start with a slight motivation. So the key motivation, as Stella already explained, is that in HPC systems, we really have to handle the heterogeneity, which is more and more increasing. So, and heterogeneity does not only mean in the actual compute devices, so that we see processors and GPUs and maybe even more strange devices, but this also covers, for example, the memory stack, right? So we see these this non-volatile memory coming up, and the memory stack is getting deeper. So we start from caches and we end somewhere with spinning disks with many different types of devices in between. And the question is how to handle all this complexity and heterogeneity. And then on the other hand, we see that depending on the code, it might make sense to concentrate on some type of components, right? So if you have a code which really needs high single thread performance, then it does not make too much sense to concentrate on GPUs, but to go for general purpose processors. And well, also the amount of memory that you need, so that the memory capacity might decide on which type of nodes in the MSA you actually want to use. And so this, of course, all this together puts some burden on the application developers. So they not only have to understand very well their codes, but also they have to understand, so what types of hardware is available, and so what are the pros and cons of the different hardware types, and then have to find out so which hardware type matches their applications the best, and maybe even more complex, which part of the application matches it's the best. So they might have to decide how to split their codes, and which part of their codes has to run where. So in the end, for the MSA, this means that they really have to optimize their codes for the different platforms. And so since performance portability is still an open issue, so some effort has to be put into this. The goal of DeepC now is to try to ease or maybe even automatize some of these tasks, right? So to give the application developers tools which support them in fulfilling the tasks sketched on this slide. Yeah, Stella already presented you the MSA, and so even if the MSA tries to hide some of the complexity and or to express this more directly, so by adding these different modules, still, of course, the modules by itself are quite complex. So if you think about the cluster module, yeah, thinking about having the EPI processor available at some point of time, so already this node will look quite complex. So you have this all these cores available in order to do your computation, but already the memory stack is a bit more complex, because it's planned that you have, besides the standard DDR memory, also high bandwidth memory. And of course, you have to find out, so what part of your data has to reside where. So yeah, try to have your hot data in the high bandwidth memory while leaving the other data in the DDR memory. And then, of course, you have to find measures on how to exchange data between the two memory types. If you look into the booster, so you have a similar situation. So you might have multiple GPUs with all having their own high bandwidth memory, but of course you have to have the CPU in order to manage the node and in order to orchestrate the GPU tasks within the node, and you don't want to handle this yeah, at the very low level, but you want to have some runtime which supports you there. And then last but not least, if you look at something like the data analytics module, so nodes there typically have yeah, different types of memory, so maybe even non-volatile memory in order to increase the memory capacity. Yeah, of course, there is a CPU, but this might be accompanied by one or more types of accelerators. And of course, you have to find out on how to orchestrate all these components within the node. So the situation an application developer is confronted with is, well, so that there is some hardware in your node, so the node you have chosen in order to run some part of your application. Of course, there is an operating system, and you want to bring your application or your workflow into this system. And then the question is, yeah, what type of programming model you want to use, on what has to be the structure of the programming model. Of course, all the programming models bring with them some time of runtime, but typically these runtimes are component specific. And component in this case means not only the type of model you are using and the type of hardware you want to use, but of course this might also be specific to the programming model that you want to use. So in the end, both. So the user and the system software developer end up with an kind of n by m matrix, right? So you have a number of programming models. You have a number of hardware to support, and that there is a matrix which not necessarily has to be fully populated. So if we think about programming models, so what are the standard models we are currently thinking about? Well, so if you look within a node and you want to handle the parallelism within the node, so a standard answer today is something like OpenMP, but there's also OmpSs by Barcelona. Or that there is a different approach to tasking developed by Fraunhofer called GPI. So GPI is special in this case because it does not only handle parallelism within the node, but also across the node. So it's a kind of bridge between the OpenMP or OmpSs and the MPI. And of course, MPI is still is the standard answer to the question, how do I distribute my application across a system with distributed memory? And well, we think that this will be the answer also for quite some years, so especially until we reach actually Exascale. But there are other approaches which are more high level, so which try to kind of cover these different levels of parallelism in a more abstract way, so that you get into the area of domain specific language. And so one example we have within the project is this NabLab approach developed by CAA, which tries to give the programmer a handle to do the programming in a way that it's like just writing down mathematical formulas. So if you think about the NabLab calculus, so this is the motivation for this name. So you have the NabLab calculus write just down your differential equations, and then there is a mechanism in behind which creates efficient code from your formulation of the problem. So how is the actual project structured? So we found out in the deep series of project that really applications are a key part of these projects. So the applications on the one hand set up the requirements that the software stack has to fulfill. On the other hand, of course, these are the benchmarks in order to find out, so is this what we develop within the project actually suitable in order to serve the applications? And for this reason, we have this work package containing the applications in order to provide the mechanisms I just mentioned. Of course, so we don't want to enable all the higher level work packages to directly act on the hardware, but we introduce a kind of abstraction layer in between. So handling, or acting as a kind of operating system, so not operating system in the stronger sense, but more a kind of providing services or operating system like services for the higher level components of the software stack. And so basically this WP this work package 3 with system software tries to cover this NYM problem, which I mentioned on the slide before. Then of course we have to concentrate on 2 parts. So one part is so what is the programming model, and what is the runtime which acts on the nodes itself. So to especially in order to handle the memory complexity on the nodes, which is popping up currently. So we have reserved one work package for that, and there is a second work package, so-called work package 5, which handles the module-wide or the system-wide programming models. So of course, most prominent, there's MPI here. And the idea in the project is that we want to follow the developments currently going on in the MPI field. But we also look into alternative approaches, right? So of course there has to be a connection to the say global OS, which we think PMIX will be the answer to, but also something like an extension of the OmpSs system across node. So something like cluster OmpSs, or this idea of GASPI and GPI space developed by Fraunhofer. And the idea within the project is to try to mix and match all these components and to leverage synergies in between these approaches. So for example, to use common runtimes, or to reuse components of the different runtimes in order to fill this N/M matrix that I mentioned. And last but not least, and Alex will go into more detail in the next talk, is about tools. So to really help the application developers to do their works, so to do their analysis work, to do their to help them to draw conclusions from the analysis and to decide how to split their applications. Last but not least, we are in an, as Stella already mentions, we are in an environment of other projects, so especially the 2 sister projects, IOC and RedC, and of course we will interoperate with them. So for example, we will not concentrate on IO, but we will work together with IOC in order to handle all the IO challenges that we have to face. So what do we want to cover within our software stack? So one key objective is the efficient use of memory. So to use the OS in order to do the memory mapping, to access performance counters. We also want to look into something like processing in memory and figure out, so are there any opportunities which are feasible in the runtime of the project. And so one different aim of efficiency will be to really be energy efficient, right? So of course you have to decide where to run your code, and one constraint that you have there will be to choose the platform or to choose a module which is most energy efficient for your code, and still fulfills constraints like that you might have limited time to solution. A different objective will be that, of course, if you have this modular approach, scheduling and resource management will become more complex. So the idea within the project is to do this Slurm based, and but as we see today, Slurm does not cover all the requirements that we have, and so the idea is to, especially if you think about application workflows, to add support to Slurm, to really improve the scheduling decisions made by Slurm. As I already mentioned, so we want to work together with IOC. So one topic there will also be that so IOC covers this PEACOG approach in order to act on an HPC system like in a cloud and to deploy virtual machines to the nodes in order to have a higher level approach to packaging of your software. So this slide summarizes the programming environment that we want to present to the applications. So I already mentioned all these programming paradigms that we want to cover. But not just to implement them, but of course also to enhance them. And so the aim of the project is then to in order to make this more supportable, to push these modifications into the corresponding standards. For Exascale, we think that malleability will be really crucial, and so that there are approaches to standardize this in MPI 4, and so the idea of the project is to really follow this standardization and also to be part of driving this. I already mentioned the performance portability, and our approaches there are NabLab and DaCe. So to be able to generate executables for the various targets, so the various modules in an automatic and performant way. And last but not least, so resiliency will also be important. So we are looking into checkpointing with and leveraging for this the deep memory hierarchy that we have with most probably also non-volatile types of memory. This is what I wanted to present. I think I already run out of time, and so now I hand over to Alex in order to give you some insight on what we want to do on the tool side within the project.
Thank you, Norbert. So I will just share my screen. 1 moment. So I hope you can see my screen. Perfect. So I will tell you more about the performance analysis and modeling tools that we will develop, extend, and use in the DeepSeek project. So first, let's take a step back and look at what we want. We want our applications to be correct and fast. Also on our heterogeneous nodes and our modular supercomputing computers. So in addition, we want our applications to run in a most efficient way. So we have to find out how we map our applications to the actual hardware to reach all these goals. And it's a bit much to ask the user to do all these to tackle all these problems. So we need tools to make this happen. So Norbert already presented to you the basic structure of our environment. The tools will integrate with this structure, and we will start with the application analysis tools, because we need data about our applications to actually do anything with regard to finding out how our applications perform and what we can, where we can optimize them. So the first part is the application profiling, tracing, and debugging. So we will reuse existing methods and tools, and we will increase the awareness of the modular architecture of the new supercomputers. And we will mainly focus on tools for data transfers, because data transfer is one of the most crucial points in a modular structure. You have to consider the data at different levels. So we will provide tools that will provide access to new hardware counters and the intercommunication between the different MPI nodes. We will provide tools that help us to do an analysis of memory accesses. We will provide tools that simulate heterogeneous memory hierarchies and also simulate the access or the computation on large hardware accelerators. In addition, we will provide extensions to the actually existing programming tools on a higher level. For the example, the stateful data flow multiprocess, which we will enhance to give us performance and debug info, so we can analyze all the behavior of these tools. Finally, we will provide a tool to help us analyze remote memory accesses and debug the communication between them. These were the tools the user has to use explicitly. In addition, we will provide tools and to monitor systems and applications while they are running in the background. And we will monitor different things. We will monitor at different levels. We will monitor, for example, energy consumption, or we will monitor system throughput and also consider the application at the same time. All of this monitoring data will be collected in a central database where we can have a look at this data to analyze how our system is performing, and we will provide this we will augment this provided data with data from the node level and the application level, such as job details, performance data from the instrumented applications, so that we can find the relations between the system performance and the application performance. And all this data will be provided to the user as an analytics tool in a job-centric information platform. Now that we've seen the first part of the performance analysis tool chain, I like to say, what are we going to do with all the data we collected? Well, it's nice to look at, and you can see how your application and system behaves, but there's more. We can use the data we gathered to, and additionally, the knowledge we have about our system architecture to generate models of our system and of our applications, how the application behaves on our system. So let's start with that. We will provide models and tools to generate these models that will help us to describe performance and energy consumption depending on the execution configuration of the application, or also the properties of the system. We will also consider the impact of hardware latency and bandwidth in this context, and provide tools to help us describe the application behavior on our heterogeneous systems. In addition, since GPUs and other accelerators are a main point of the modular architecture, we will provide predictions of the application requirements for applications on these GPUs and other accelerators. So what are we going to do about the models? As I already said, we will provide models, but models can be just models and also simulation. So simulation is more concrete in this in the kind of information that it will get us, but it's also more effort. So the first model we are going to present is about performance and energy consumption of computational patterns that often occur in various programs and applications. The next model we will develop is an empirical model for GPUs, where we'll consider computation and data transfer between GPU, CPU, and more. And also we will provide a model for heterogeneous memory systems, but we will not only provide a model, we will also provide a simulation of the heterogeneous memory systems, so that we can see how the memory transfers in these systems occur and what they are made up of. So we will use simulation also to provide an analysis of workload interactions on numerical accelerators, and we will extend or develop simulators so that we can evaluate various processing in memory approaches to get a better understanding of how they will be we can use them in the future architectures. So now that we've seen that we have some models and we've gathered the data to provide generate these models, what are we going to do with the models and the simulations? As already mentioned, we intend to map our application to the different modules of the architecture. And that brings me to the question, how do you run an applications on a modular supercomputer? Well, you have many choices. You have to choose what system modules to use. You have to choose how you want to configure the modules. Where do you want your parallelism to be? And remember, you want your application to run efficiently. So you have to support the user in making such decisions. Because you have so many decisions to make. So how can we use the application, the models and simulations? So we thought it would be a good idea to have the empirical requirement modeling, which has less effort than a simulation, to provide an idea or to provide a model how the application behaves at the system level. So it's more coarse, it's not fine-grained at the node level, but it means less effort, a bit inaccurate, but enough to find out which modules to use. You can use a simulation, which is more accurate, to get a fine understanding about the data movement and locality effects at the node level. And in addition, we will provide what-if scenarios where we can check how the application and system parameters impact the performance of the system. So with all these models and simulation, we will build a mapping tool chain, which ties all this together and which will identify which modules and execution parameters are ideal for your application and input problem. This will be built around the Exascale tool, and it will help us to project the hardware requirements of different workloads into the future. And it will help us design in this way the next generation systems and extensions to current systems. Furthermore, it can also be used to tell us more about how well our code fits the current architecture, and you can use it to tweak our application code. Finally, we are going to analyze the mapping decisions of the tool chain to help us optimize the design of future architectures and to validate our approach. So now we've seen all the tools that will help you to create and to your applications and achieve your performance goal. We have seen the application analysis tools, which will help you to collect the data, the job performance data and the performance data of the system and application. We have seen how we will predict the behavior of the applications on bigger systems, and the relation between the application performance and the underlying system. And we also have seen that it's important to have a description of your architecture that can help you to generate all the models and make and suggest or find an ideal mapping of your application to the underlying system, so that you can find the sweet spot for code and application distribution for any of your problems. So that was my part in this presentation, and now it's Olivier will tell you more about applications.
Hi, I'll share my screen. Yep. Which you can hopefully now see.
Yes, there's some noise in your mic for some reason, so there's some static noise.
Static noise in my mic. Let me try and mute and. Is this any better?
It feels the same. I think that we have to leave this way, I guess. It sounds like if you were close to a train passing by, but I hope it's okay. I hope it's understandable.
Oh dear. I've just realized it might actually be my laptop fan. Apologies, that's going to be hard to fix for me. Right, well, I'll do my best. So the applications, the co-design applications, of which there are 7, I see their role as being asked to illustrate the quality of the concept of MSA as a whole in achieving good node-level performance, demonstrating the impact of contributions from Work Package 4, achieving also good cluster-level performance, which stresses the communication side, and developments in Work Package 5, and all of this thanks to the tooling, the profiling and performance assessment tooling developed in Work Package 2. So the applications have been chosen to cover the main programming languages which are found in HPC nowadays, I guess, Fortran, C++, and Python. There's a range of different kinds of algorithmic difficulties involved. There's a range of parallelization strategies that have been deployed and data usage patterns. Sorry, the work package will also be responsible for providing low-level and synthetic benchmarks of the underlying software stack and system. So if I go through the applications now, we have a space weather theme, which is driven by the University of Leuven, with a pair of codes, XPIC and IDA-Pi, one being a particle in cell simulation code, C++, with hybrid parallelism, and it's paired with a pre and post processing code based on machine learning. And so this is an excellent example of a workflow which should conceptually map really well to the MSA design. And they will be looking in DeepC at new parallelization alternatives to those that have already been implemented in improving the offloading acceleration, which they have, very clearly managing, mapping the data flow of from their workflow onto the MSA software stack as well as possible. They will be using the performance analysis tools that DeepC will be working on, and the job scheduling, which ties in with the data flow point. These are their main axes for DeepC development. Going from space weather straight to terrestrial weather, the IFS is ECMWF's weather prediction software suite, based on spectral semi-Lagrangian dynamical core. It has hybrid parallelism again. It is Fortran, and it has partial OpenACC offload. And we will also be using a set of mini apps, which in which algorithmic meteorological algorithms have been extracted from full applications, and for a number of them, there are a range of technical implementations. And so in DeepC, we will be looking at, in particular, at what we can do with the memory management tooling, which DeepC will work on. How we can more efficiently distribute work and offload work, be this with OpenMP offload, OmpSs, or also for the full IFS MPC, which should map very well to our hybrid MPI and OpenMP usage. And we'll have a strong focus on getting as much, providing as much feedback as possible to the tooling work package. There's a seismic imaging theme driven by the Barcelona Supercomputing Center and by Fraunhofer. So there are two apps here, both of them reverse time migration implementations. So there's BSIT and FRTM. And for BSIT, memory hierarchy and I/O on the heterogeneous memory, which will be available on the platform, and the tools to specify access to this will be looked at for BSIT. And FRTM will focus more on scheduling of malleable jobs, so relying on the malleable MPI and GPI developments, which should go on in the projects, and synergies with the overall MSA design in terms of mapping complex workflows to the system. On the molecular dynamics side, GROMACS, everyone has heard of GROMACS. KTH will be pushing developments for this biodynamics code, which makes heavy use of 3D fast Fourier transforms. And in DeepC, a new FFT library will be developed with the aim of achieving maximum performance thanks to the MSA tooling and hardware. They will also be looking at using DaCe to achieve performance portability on a range of hardware which should be available inside the project consortium. KTH is also bringing NEC 5000 CFD code to the project. It is a large Fortran code, parallelized in this case only with MPI, no OpenMP, and it has OpenACC and CUDA offload. So in DeepC, they will be looking at achieving a full port of the program to large heterogeneous systems, with a particular focus on heterogeneous memory and GPUs. And they will also be looking at DaCe usage, and this will be interesting because DaCe and there probably haven't been many examples yet of DaCe being applied to large Fortran codes. We have a code in the field of neutron transport, relying on a Monte Carlo method. C++, hybrid parallelization, worked on by the CEA in France. And this code, Patmos, will be ported to the MSA software stack and hardware. And they will be focusing on the explicit use of the heterogeneous memory stack and the heterogeneous compute units. So making best use of the available heterogeneous resources on the system. And finally, Earth system modeling, driven by Jülich. The TSMP is a regional Earth system modeling platform, an MPMD application by nature, workflow, if you like. It relies on OASIS to couple 3 separate components, which are not all written in the same programming language. They don't all have the same parallelization strategies or offload capacities. So it's a very interesting workflow for the MSA approach, which DeepC is pushing. So work will focus on each of the Earth system model components in tailoring them to MSA partitions, the most appropriate partition for each of the separate applications. This will also involve enabling or, in some cases, improving the GPU usage of some of the components. So some of the atmospheric component, for example, already has a GPU offload capacity. And there will be extensive use of the performance profiling tooling to optimize the full workflow on the MSA system. So that's it for the applications. I will stop sharing my screen.
Thank you very much, Olivia. So with this, we are through the presentations. It took a bit longer, sorry for that. Are there any questions? And feel free to either post them on the chat or speak up. I think that you would need to be authorized for that, but you can raise your hand and then we give you the right to speak. In the meantime, while you're maybe thinking of questions, I put on the chat also a link to Gather. So we will be there after the session for more informal discussions if you want. So let me see the first question. So is there a fear of reduced overall system utilization as the scheduling problem becomes more difficult on MSA systems? This problem should get worse with the number of modules and the number of applications using a changing set of different modules. Do you have scheduling algorithms in mind to deal with this? So I think that Norbert, this is a question maybe for you. Or Manolis, would you? Yes, unmuting is better.
You cannot.
So maybe Norbert, you can say a word and Manolis will add then on that.
Yeah, so first of all, I have to just found where the questions are. And it was too long to just understand it. Well, so
Norbert, it's under the QA control.
Yeah, I found it, but I have to read it because it was too long to to really understand. So Estella read it. Yeah, of course. So well, so if you think about workflows, of course you always have the issue that the that the overall utilization gets worse because your scheduling problem becomes harder, and this is the reason why we look into that. And yeah, of course that there is a fear that the overall system utilization gets reduced, and this is the reason why we look into that in order to try to compensate that scheduling decisions of course become more complex if you have a more complex system architecture. Yeah, but yeah. So this, but in the end, so this is an open question, and yeah, needs investigation, needs research, and this is the reason why we look into that.
Manolis, would you like to complete?
I would probably build on Norbert's initial response. So we expect that there will be workflows and there will be, let's say, modules that correspond to, let's say, significant phases of these workloads. So there is a danger of, let's say, underutilizing the resources. On the other hand, the workloads are getting the opportunity to actually use very distinct types of resources from a single entry point. And I think that's one of the major challenges that we will need to handle with the job scheduling extensions that we are considering. And perhaps I think also the applications that we have in the project are going to challenge us quite significantly. So no clear technical answer to the colleague that posted the question. I'm just saying that this is precisely the framework where we will be working on. And I think workflows and staging of data, etc., necessitate having a modular architecture. And I think that our plans, at least for the job schedulers, will be able to provide opportunities to have good utilization. And ease of use to some extent covers that question to some extent, like the workflow will be able to use heterogeneous resources. I don't know, Estella, if you would like to fill in, or other of the panelists on this.
No, I think this is okay. I hope
I can I speak?
Yeah, Pascal wanted to
Bonjour.
Yes, right.
Yes, I think it's really important to see that we have two levels of heterogeneity. We have a level of heterogeneity that application will need to manage, but we have also the application itself that is different with a specific workflow of application. So for that, we really need to understand the two levels, because we will have something that is the workflow of the application that we need to manage, but we have also some orchestration levels that must be coordinated with the resource manager to be able to run the different workflow in competition on the supercomputer. I think we will have step for that, because we see when we discuss with people that work on this topic that we have, the first is really to have just an export of the information about the different resources that are available to more have dynamicity in the different components that need this information. So we have the application with the workflow of the application that needs some information. We have the resource manager and the orchestrator. So PMIX, for example, is one piece of software that will help to exchange information. And with that, we will have much more dynamicity to work together on the resources that are available on the supercomputer. And I think that many research is done today on this topic, and its MSA will be a good infrastructure to test all this new topic in the future.
Okay, thank you, Pascal. So Salem, I give you the mic option if you want to follow up question, or if this answers your question. You can speak up.
Yeah, so my question was exactly, I think my question was very well answered. Yeah, it is an open topic and an open question. I think most probably what I expect as well is there are other options, like middle options, such as degrading the performance, such as stopping the workflow at some point due to the fact that certain resources are not available, things like these. So I'm really looking forward to the results on this subject. Yeah, thanks for answering my question.
Thank you. Any more questions? So it does not seem to be the case. So again, you can find on the chat a link to Gather Town, so a nice app that the colleagues at HiPEAC have put us at our disposal. So I can show you how these things look like, just that you know. Okay, let me close all the other windows. I hope you see my screen. So basically this is us, we are in a room. If you are curious, if you would like to speak with us, ask any other questions, feel free to connect to the link, and we will be there for the next 20 minutes or so. If somebody comes up, we can stay a bit longer. So thank you all of you for attending. Thank you for your interest. If there are any additional questions you would like to discuss, we will be there, and see you then hopefully in the next HiPEAC session. Thank you.